we have learned that enols are useful reactive intermediates because they are nucleophilic, and we have learned two ways or two methods for making enols from carbonyl compounds with an alpha hydrogen. It is possible to make enols from carbonyl compound with an alpha hydrogen if the carbonyl compound is treated with a catalytic acid or catalytic base. We have worked out mechanisms for both methods. And again, as we have said before, what is special with these intermediates anyway? So why are they important in synthesis or in chemistry as a whole? Well, enols, as we have learned before, they are nucleophilic. Let's draw the structure. Draw the structure of enols and see what we can do with it. So this is the enol structure. Enols are nucleophilic, and they are nucleophilic at the alpha carbon. So that's if we take a lone pair from that oxygen and try to delocalize the electrons. So we can make a double bond, therefore, between oxygen and carbon and simultaneously break the carbon-carbon double bond. If we do that, then we get this resonance form. Which has a lone pair on the alpha carbon. So this gas, that alpha carbon, is actually nucleophilic. This is also called alpha carbonyl because there is a carbonyl on the alpha carbon. It is nucleophilic because it has a negative charge. So this carbon is nucleophilic. So that's why, therefore, enols are nucleophilic because of this resonance. They are nucleophilic at the alpha carbon. And if they are nucleophilic, therefore, they can react with electrophiles. So if the enol, so this is a proof, if you like, that enols are nucleophilic and they are nucleophilic at the alpha position. If you take an enols, and you react this with an electrophile, we can do something very similar. So we can take one of the lone pairs on oxygen to make a double bond here, and then we break this carbon-carbon double bond and simultaneously attack the electrophile. E is for an electrophile, or stands for an electrophile. The product that's obtained is this one, where this alpha carbon is now bonded to the electrophile. So therefore, that is the new bond. It could be a new CC bond if the electrophile is an alkyl halide. It could be a new CC bond if the electrophile is another organic electrophile, such as an aldehyde or a ketone or a carboxylic acid derivative. Now, this intermediate can lose a proton by a conjugate base, so a B for a base, a general symbol for a base. The base can now come, take off that hydrogen, breaking the hydrogen-oxygen bond, releasing electrons on the positively charged oxygen. So the final product is this one, where the alpha carbon has bonded with an electrophile. So this is a general representation, if you like, of the chemistry of enols, the fact that they are nucleophilic on the alpha carbon or the alpha position because of resonance, and because of that nucleophilicity of that alpha position, enols can react with electrophiles in the way it is shown to give a final product of this type. So therefore, enols are very useful reactive intermediates because they are nucleophilic, and because they are nucleophilic, therefore they can react with electrophiles.